Hey everyone, so today we're going to be building a neural network with PyTorch. Neural networks are a really big deal in the fields of artificial intelligence and machine learning, and among the many applications of these neural networks, one of the most foundational and beginner tasks is handwritten digit recognition. This tutorial aims to go through the process of building a digit recognizer using a neural network, and I'll go through the code line by line so it's totally understandable. We're going to be using the MNIST dataset, spelled MNIST, which is a common benchmark in this field, and it consists of 70,000 handwritten images. So by the end of this video, you'll have a thorough understanding of how to construct, train, and evaluate a neural network designed to recognize these digits with impressive accuracy. So the first thing we're going to do is import the necessary third-party libraries. NumPy for mathematical operations, PyTorch for actually building out our model, pandas for data processing, data handling, and matplotlib pyplot for generating figures. The next really important thing we're going to need to do is set random seeds for reproducibility. So what does that mean? So when we set random seeds for reproducibility, what happens is we pick a number, we're going to pick 42 in this case, and every time a random process happens on our machine, for example with NumPy or with PyTorch, it's going to be the same every single time, and it's going to be the same on my machine and your machine if you use the same seed as me. So we're going to set the seed to be seed 42, and we're going to just copy and paste. We're going to seed NumPy and PyTorch as well as CUDA if you're using a GPU. The next thing we're going to do is load our data. So let's just set some markdown here saying we're going to load data. So the first thing is we have to load our data set. And first, let me just take you through what the data set looks like. So I have the data in the data folder here, and it's from Kaggle. I have the link here, and I'll put the link in the description as well. But essentially, it's 70,000 images split into a training file and a test file. We'll deal with the test file later, but for now, the training set has 42,000 images and the test set has 28,000 images. The data is formatted as a CSV, which is a comma separated values, with a label column, which tells us the digit that each image is. So we have the label here and 784 columns, each with a pixel value. Pixel 0 to pixel 783 are the columns. And each contains the pixel value at the specific pixel between 0 and 255. So 0 is going to be black and 255 is going to be white. And you'll see any value in between that range. So these are grayscale images, which is why we don't have the red, blue, green. We just have a range from how white it is to how black it is. So though the data can be visualized here as a spreadsheet, it's actually a CSV file where everything is separated by commas. So if I open it up as an editor, you'll see here that everything is separated by commas. And it's the same in the test as well. And the reason why knowing that it's separated by commas is really important because of how we're going to load our data. So we're going to set the data set to be this value. So we're going to use the NP, the NumPy load text function. We're going to load in the data / train CSV file, which is delimited or separated. Each value is separated by commas. And we're going to skip the first row. And the reason why we're skipping the first row is just the name of the columns here. We don't want that. We just want the values for our data set. Next, we're going to split this train data set into X and Y. So X is going to be our independent variable, which are the pixel values, and Y is going to be the dependent variable, which is the which digit it is based on the pixel values. So X is going to contain every single row of every column except the first column. So X is going to be equal to dataset, every single row with every column except the first column, because the first column contains the label. And we can print X to see what it looks like later. And Y is going to be dataset, every single row, and the first column. Remember, it's 0 indexed, which is why we're using 0 and we're using 1 here. Every column from 1 forward. And we can print Y here. So let's go ahead and run the code here. Remember, we have to run the dependencies, run the seed, and run the data. So what that looks like is we have an array of arrays for the X, because each row is going to be its own array. And we have an array of output values, digit values. So 101, 101 here. It aligns, and that's what the X and the Y look like. So I told you that these are images, and the train.csv file doesn't look like it's made of images. It's made of values that represent the value of each pixel. But let's visualize what the data actually looks like as an image. So let's visualize 10 different samples, and we're gonna pick random values, any random 10 images from the range length of X. And the length of X is, again, it's 42,000 because we have 42,000 images in the train set. And from the 42,000, we're going to pick 10 samples. And we're gonna make sure that we're not picking the same sample more than once. So we set replace equal to false, so that we're not replacing the value in the distribution. We're picking different values each time. And we're gonna pick 10 images based on the 10 random numbers that we chose and their corresponding labels. There we go. So we've basically picked 10 images as well as their 10 corresponding labels. And I'm just going to copy and paste in the code that I used to visualize the samples. So you can copy this code if you'd like, but it's mainly for just demonstration and visualization purposes. So here we go. We have image of an 8 with the label 8, label 1 with an image 1. Every label in this is going to be correct because it's from our training set. We can rely on our training set to have correct labels. Now the next important thing we're going to want to do is, as you know, the values of each pixel are in between 0 and 255. So this is quite a wide range, and it makes it difficult for the internal calculations to deal with large values. So what we do is, in data science, we normalize the values. So what this does is, when we divide by 255, we set the range of 0 to 255, we squeeze it down to be 0 to 1. So now if we print, let's print the non-zero values of x. So for num in x 0, the first row of x, if num is not 0, let's just print num. So previously, when it would have been from 0 to 255, we now see that it's in between 0 and 1. And just to verify this, let's see what it looks like before normalizing. As you can see, it's values from 0 to 255 before normalizing, and after we normalize, it's in between 0 and 1. let's just get rid of that and get rid of that. Okay. Next, before we get into the juicy bit, which is actually writing out our model, we have to make sure that our data is compatible with PyTorch. So we're going to use something called tensors. You may have heard of TensorFlow. It's named after tensors. So let's say you have a 1D array. That's a vector, one vector. You can also have a 2D array, which is a matrix. And you can have a 3D array, which is an array of arrays, and so on infinitely, theoretically infinitely, for n dimensions. So a tensor is just going to be an optimized matrix, an n-dimensional matrix, to put it simply. So we're going to set x to be a tensor, and this is how we do it. We also want to specify that it's 32-bit floats, because we've normalized it to be decimal values in between 0 and 1. And y is just going to be any value from 0 to 9, because those are the digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Torch tensor, and this is how we do that. 64. So they're just integers, and we'll run that. And now we're going to get into the juicy bit, which is defining our model. So let me just set some markdown here. PyTorch model. Great. Okay. So our model, let me just talk about it first. Our model is going to have 784 neurons as input, be one for each input, each pixel value, and it should have 10 neurons as output, one for each handwritten digit, 0 through 9. So we're also going to have hidden layers in between, and the neuron values for hidden layers are kind of arbitrary, but there are some rules of thumb to decide how many neurons to have in each layer. But we'll just pick, we're just going to go with 300, you'll see later. So we're going to set the model to be a sequence of layers, and then sequential, and then the first layer is going to have, as I said, 784 input, and we're going to go with 300 outputs. It's going to output to 300 different neurons, and we're going to use an activation function called the rectified linear unit, or ReLU, and I'll explain and show a graph of what that looks like and what it does later. But for now, let's just go with, and then ReLU, and linear 300. The other hidden layer is going to have 300 inputs and 300 outputs, and that's also going to have a ReLU activation function, and our final output layer is going to have 10 outputs, one for each digit, and that's our model. It's pretty simple. It has 3 layers. The input layer 784, the middle layer with 300 neurons, and an output layer with 10 neurons. That's it. And even with this, we're going to get pretty good results and pretty high accuracy. So what is ReLU? Each neuron in the network needs an activation function. So how much a neuron should activate is based on its input. It's based on an internal calculation of input times the weight of the neuron plus the bias. So each neuron has a weight and a bias. They're initially randomly initialized, the weight and the bias. And as our model trains, these weight and biases become more optimized. They become better and better at representing our data. So what ReLU will do is, it's one of many activation functions. This is what it looks like graphed. If the neuron has a negative output value, it's just going to output 0. And if it has a positive value, it's going to output that positive value. Y equals X. It's going to be exactly that output value. So this is one of many activation functions. So hopefully that made sense. So if that didn't make sense, I'm going to make a video series on machine learning as well as deep learning. So definitely stay tuned for that if you want to learn more about machine learning techniques as well as neural networks. But yeah, essentially that's it for our model. The next thing we're going to do is define the loss function and optimizers. So as I said, the weights and the biases are randomly initialized, and as our model trains, they're going to get better and better based on our loss functions and our optimizer. So the loss function is also known as the error function, which quantifies how well a single prediction of the algorithm is compared to the actual target value. So it quantifies how much the error is in the prediction versus the actual value. And the optimizer is the function that adjusts the attributes of the neural network, the weights and the biases, to reduce the loss, reduce the error rate, and which in turn improves the accuracy. So here's how we code that out. We're going to set a variable loss function equal to cross entropy loss is the function that we're going to use. It's a specific kind of loss function, which is called binary cross entropy. And our optimizer is we're gonna use an atom optimizer. It's called atom. There's a few different kind of optimizers. There's very many actually. There's stochastic gradient descent. There's atom W. There's atom, but let's just go with atom. So the parameters to the function are going to be model.parameters, and the learning rate is 0.001. So we chose 0.001 as our learning rate. The learning rate is essentially how quickly the optimizer is going to change the values, which is how quickly our model learns. And generally, you can experiment with values less than 1 and greater than 10 to the power of -6. I typically move between 0.1, 0.01, and 0.001. And it's really an art, because if you make the learning rate too high, your model will learn too fast, which may sound like a good thing, but your model will basically overshoot and change the model too much, and you're going to get worse performance. And if you make the learning rate too low, your model is going to learn too slowly, and your model won't learn fast enough at all. It's going to take a bunch of iterations, a bunch of epochs to learn, when it could be learning much faster with a higher learning rate. The next thing that we're going to do is we're going to run a training loop so that our model can iteratively learn in a loop. So what we're going to do is we're going to have 10 epochs or 10 iterations of learning. In production, this value is going to be way higher, hundreds, thousands maybe. But just for demonstration purposes, only 10 epochs, and we can even achieve pretty good accuracy even with only 10 epochs. We're going to have a batch size of 10, which means our model is going to take in 10 inputs at a time. And here's our loop for epoch and range and epochs. So let me just explain what's going on here. So in each epoch, the data set is going to be divided into smaller batches with a size of 10. And for each batch, a forward pass is performed to predict the outputs using the model. So after we predict the outputs using the model, the loss or the error rate is going to be computed between the predicted and the actual labels using our cross entropy loss here. And let me just give you a quick definition of what gradients are. Gradients are measures of how much the loss changes with respect to each model parameter, weights and biases. So they guide the adjustments needed to minimize the loss and improve the model's predictions during training. So after computing the loss, the gradients are reset to 0 and back propagation is performed to compute the gradients of the loss with respect to the model parameters. And the Atom Optimizer updates the model parameters based on these gradients. So we have our training loop here, and we're going to have another loop because we're going to be giving in 10 inputs at a time. We're going to be giving in the inputs in batches. So we have a loop for that. And x batch is going to be equal to x. So here's the batch of the images as well as their corresponding values. And as I said, we're going to have a forward pass. So we're going to predict, the model is going to actually predict the values based on the input, which is going to be x batch here. Then we compute the loss using the loss function. And the parameters into the loss function are going to be the predicted values as well as the actual values. And then we're going to do a backward pass and optimization. So we set the gradients to 0. Then we do back propagation. And we take a step with the optimizer. And here's just a print statement which is going to tell us the loss after each epoch. So when I run this code, what's going to happen is our model is going to train, our model is going to learn. Hopefully there's no issues. So I'm currently training on a CPU, which means it's going to be way slower than it would be on a GPU. But while it trains, let's just write the rest of the code out. So we're going to actually need to evaluate the model and evaluate its accuracy once it's done training. So after it trains, we're going to set torch to no gradient. Why? We evaluate a neural network model by first disabling the gradient calculations to conserve resources, and because we don't need to calculate the gradients when we're actually evaluating. Our code then makes predictions on the input data x and converts these predictions into class labels using the torch argmax function. I'll explain how that works in a bit. Predictions equals torch argmax ypred dimensions equals 1. So what the argmax function does is we have 10 output neurons, and if the neural network takes an input of 9, for example, the output neuron corresponding with 9 is not going to be the only one that has an output. The other neurons are going to have an output as well, but we want to consider only the neuron with the highest activation output, which is going to be if it works properly, it's going to be the neuron corresponding to 9. So that's why we use the argmax function. And the accuracy is just going to be it's going to compare the predicted labels with the true labels y, and then calculate the accuracy of the model, which is the proportion of the correct predictions. So this is going to give us our accuracy of our model, but let's say we want to actually use our model to predict values. We're going to use the values in our test set, which have pixel values but no label. So we're going to use our model to predict the label. And you can also see that the first epoch is finished. It has a loss of 0.008687. And as it keeps going, the loss is going to decrease. So we want to use our model to actually make predictions. The first thing we want to do is load the test data set. For us, it's going to be in data test.csv. Again, this is from the Kaggle. But for your purposes, you would load it from a file or whatever you have prepared. And we're going to make it into a data frame using pandas. Test data. This is different. This is another method of formatting our data set. We're using a data frame from pandas. Previously, for our training set, we used np.loadText. Either work. Just showing you different methods. The next thing we're going to want to do is prepare the test data. So like we did with our training data, we're going to want to normalize the values as well, to normalize the pixel values. So test x is equal to test x divided by 255.0 to normalize. And again, we want to make it into a tensor. Next, we're going to set our model to evaluation mode. With the eval function. And then actually make predictions. So again, with Torch, we disable the gradient calculations. We use the model on the test x. We run the model on the test x values. And the predictions are going to be, again, with the argmax. We only want to take the output of the neuron which had the highest output value. Dot numpy. And we're also going to want to create a data frame with the image ID and label. The reason I do this is because if you want to submit your predictions to Kaggle, you have to have a output file which has the image IDs and the predicted labels from the test set. So before we create a file, we just create a data frame with image IDs np.arrange So assuming the image ID starts from 1, and it does, we're going to create our data frame with the pandas.dataframe with a column called image ID which contains the image IDs, and with a label column, which contains the test predictions. Close that, and then we're going to save it to a CSV file. We're going to call the CSV file submission.csv, which is what is required by Kaggle, with the index false. So let me just explain what happened in this code. So we're loading our test data set, we're normalizing the pixel values like we did for the X of the training set, we're converting the model to evaluation mode, then making predictions on the test set, creating a pandas data frame with the image ID and the predicted label, and then saving the data frame to a CSV file. So after this, after the model is done training, I'll run the code, evaluate it, and make the predictions, so we can see what the accuracy actually is. See you then. A couple things. First of all, make sure you close this line with the parentheses, otherwise you're going to face a little error. And also make sure you add this line to print the accuracy. Otherwise you're just not going to see the accuracy. So as you can see, we trained 10 epochs 0 through 9, and our accuracy is above 99%, even though we just had 10 epochs of training. And that's all. Leave a comment if you have any questions, like if you like the content, and subscribe for any future videos. Thanks.